the first law of thermodynamics for a control value. We already considered the first law of a thermodynamic for a control mass, which consists of a fixed quantity of mass, and noted also in the previous chapter, delta E equals to heat input work output over we have also noted that this may be written as a instantaneous rate of equation. D E control mass Q rate of Q minus W, which is power. To write the first law as a rate equation for a control value, we proceed in a manner analogous to the use in developing a rate equation for the law of conservation of mass. For this purpose, a control value is shown in this picture that involves the rate of heat transfer at this point, rate of work from the turbine at this point, and the mass flows to turbines and out of the boiler. The fundamental physical law states that we cannot create or destroy energy such that any rate of change of energy must be caused by rate of energy into or output of the control value. We have already included rate of, so the conservation of we cannot create or energy such that any rate of change of energy must be caused by rate of energy change in energy rate of energy input minus rate of energy output. In the control value, we have already included rate of heat transfer and work in the equation of instantaneous rate of energy, which was dE rate of the heat input and work output, so that additional expansions we need are associated with the mass flow rate. The fluid flowing across the control surface enter or leave with an amount of energy per unit mass as the fluid is flowing across the control surface enters or leaves with an amount of energy per unit mass. As this relation E equals to for interest and mass across the control surface. Energy, specific energy per unit mass. Related to the state and position of fluid. Related to the state and position of fluid. When the flow mass enter a control volume, E with at state I we can write, for example, EI, UI, the energy of the flow mass into the control volume, and therefore the flow mass exit at state E. There is a boundary movement work associated with the process also. To explain this in more detail, consider an amount of mass flowing in the control volume. As this mass flows in, there is a pressure at its back surface, so as this mass moves into the control volume, it is being pushed by the mass behind it, which is the surrounding. The net effect is that after the mass enters the control volume, the surrounding have pushed in against the local pressure with a velocity giving it at rate of work in the process. Similarly, a fluid existing the flow, the control volume at state E must be pushing the surrounding fluid ahead of it, doing work on it, which is work leaving the control volume. So it is talk about this when we have, for example, flow in and also flow out, VE, VI, work will be down due to the pressure on back surface at point I, and also there is work to leaving mass the control line. The pressure of mass which cause due to giving the control value. The velocity and the area correspond to a certain volume per unit time. Entering the control volume enables us to relate that to the mass flow rate and the specific volume at the state of mass going in. Now are able to express the flow work as this relation. The flow work, can review that flow F V, which is integration of P, this is velocity, dA, which is P V dot. This is volume and equals to P specific volume M dot. Pressure specific volume and mass rate. For each section, for the flow that leaves the control volume, work is being done by control volume, and for the mass enter the surrounding to the rate of work. For mass flow out, we have PE E M dot E down by the control volume, and for the mass flow in PI m dot I work on the control value. The flow work per unit mass is then PV and the total energy associated with the flow is E plus PV, which is we have U plus PV GZ. E is U, this expression is H enthalpy, and we can write H GZ. In this equation, we have used the definition of thermodynamic properties enthalpy, and it is the appearance of the combination of U plus PV for the energy in connection with the mass flow that is the primary reason for the definition of properties enthalpy. Its introduction earlier is conjunction with the constant pressure process was down facilitated use the tables of thermodynamic properties at that time. To extension of the first law of thermodynamics, we can now write TE control value Q dot control value minus W dot control value. This is the external heat and external work. We have also internal cases. M dot IEI, M dot E plus W dot flow in minus W dot flow out. And the substitution, we can write this relation. It is PV DE M dot I EI plus PI specific value M dot E which they are H, I, H, E. Now we can write, no, this is not, excuse me, it is UI plus ZI plus PIVI, that these two parts HI. On the next page we can write the relation as this expression. Control value W dot control value plus dot I HI plus in this form of energy equation, the rate of work term in the sum of all shop work terms and boundary work terms and any other type of work given of the control value. However, the flow work is now listed separately and included with the mass flow rate term. We're talking about these terms and the mass flow work terms here. For the general control volume, we may have several entering in general we may have several entering or leading mass flow. So a summation over those terms is often needed. The final form of the first law of thermodynamics then become as minus ME expressing that the rate of change of energy inside the control volume is due to the net rate of heat transfer and net rate of work net rate of heat transfer net rate of work and the summation of energy fluxes due to mass flow in and flow out. mass in and mass out. The first law, general form of first law of thermodynamics. As with the conservation of mass, this equation can be written for a total control volume and can therefore be put the lumped or integral form as this relation for a total control volume MAEA plus MEB plus other, as the kinetic and potential energy term per unit mass appear together with the enthalpy in all the flow term. A shorter notation is often used as for example, H total and H stagnation point. Defining the total enthalpy and the stagnation enthalpy. The shorter equation can be written as follows. Given the general energy equation on a rate form, all application of energy equations start with this equation, and for special cases this will result in a slightly simpler form as shown in the subsequent section. This next section is the steady state process.